With every single move we make, our bodies are generating these tiny electrical signals.
Right, yeah, even just wiggling a finger.
Exactly.
Very-
From that tiny twitch to, walking down the street, it's all powered by these like invisible currents. Today, we're going to take a deep dive into that world, specifically electromyography, or EMG.
Mhm.
And building on that idea, our deep dive today focuses on a really insightful bit of tech, the EMG hand simulation tool.
Ah, yes.
Yeah, and this isn't just like a picture. It's an interactive way for you to really explore that direct link between, say, making a fist or pointing and the electrical waveforms your muscles actually produce.
And that's a really key point, actually. Understanding what it's for is just as important as how it works.
Okay.
So our mission today basically is to unpack how this tool functions, what it's designed to teach you, and maybe just as important, what it's not meant for. And we'll touch on what's coming next for it, too.
And we've got some good stuff to work with. Our sources, they include detailed notes from development, technical descriptions. We even looked at some of the actual code behind it.
Oh, wow.
So yeah, we're getting a really granular view of how this simulation actually, comes alive for you, the user.
Good stuff. So maybe let's start with the basics. What is EMG?
Good idea.
So electromyography, it's essentially the process of capturing those electrical signals we talked about, the ones produced by your muscles when they contract.
Right.
Think of it like listening in on the electrical chatter of your muscles while they're busy working.
It's almost like hearing the body's hidden orchestra, isn't it?
Yeah.
I remember when I first really got that, it kind of changed how I thought about just moving.
Yeah, it's fundamental.
And the great thing about this tool is how it makes that concept real. So it simulates the electrical activity that you would record if you had electrodes placed near the hand muscles.
Right, if you were doing it for real.
Exactly. And what's really neat is how it visualizes these signals, these waveforms showing the muscle activity, and it does it in real time as you interact. That's really the core idea it's built on.
So that's the concept. But how does it actually work for someone using it?
Well, it's surprisingly straightforward.
Yeah.
You've got this hand diagram on the screen, right?
Mhm.
You just click on a finger. That simulates it moving. And when you do that, you see the finger twitch slightly on the screen, and bam, instantly, you see a corresponding jump in the recorded signals.
So it's immediate feedback.
Totally direct. A visual link between the action and the electrical result. And if you want to go faster, there are keyboard shortcuts, numbers 1 to 5 for the fingers. Plus, it works on touchscreens too.
And that real-time visualization is,
Yeah.
I think, what makes it so compelling.
Definitely.
As you click or tap, you see those EMG waveforms changing live, dynamically responding. Behind the scenes, the code's constantly updating the data, redrawing the signal paths on the graph.
Yeah.
It creates this really fluid, live picture of what's supposedly happening electrically.
What's also quite clever is how it adapts the display.
Oh, yeah. How so?
Well, depending on your screen width, it's not just about looking neat. It shows they really thought about the user experience, keeping it intuitive no matter the device.
Oh, okay.
So like on narrow screens, say a phone, the hand diagram sits above just one combined chart showing both electrode signals, saves space, keeps it all on one screen.
Makes sense.
But on a wider screen, like a desktop, the hand's on the left, and you get 2 separate charts for the electrodes, stacked vertically on the right. Gives you a more detailed view, uses the space better.
That is well thought out. And it has different modes, too, right, for learning.
Yeah, exactly. By default, it starts in demo mode.
Okay.
So the tool just automatically runs through simulating finger movements and showing the signals. Kind of lets you just watch and see how it works.
Right, passive learning.
And this is crucial if you decide to jump in yourself, click a finger, use a shortcut.
UK control.
Demo mode pauses automatically. Then you can switch between demo and user-controlled mode whenever you want. There's a button, or you can just press the DHEMA key. Lets you learn at your own speed.
Very flexible.
So we've covered how you interact, what you see, but that leads to the big question, right? We're not actually wired up. So how does it make these signals? How are they simulated? That seems like the real magic here.
Yeah, that is the interesting part, isn't it? How does it fake it so convincingly?
Uh-huh.
Well, when a finger gets activated in the simulation, the tool applies specific preset amplitude patterns. These simulate what the 2 virtual electrodes would be picking up.
Okay, amplitude patterns. What does that mean exactly?
So these simulated signals, they're generated by combining mathematical functions, things like sine waves, but then crucially mixing them with random noise.
Random noise. Why add noise?
Well, that's actually key to making it feel more real. Real biological signals are never perfectly smooth or predictable. They're messy.
Ah, right. There's always background interference.
Exactly. So adding that randomness, that noise, on top of a base signal makes the waveform look much more like something you'd actually record. It also subtly teaches you about the challenges of interpreting real EMG.
Gotcha. And you mentioned specific patterns.
Yes, they've defined specific amplitude values for each finger across the two simulated electrodes. For instance, activating the thumb gives electrode 1 an amplitude of 3, and electrode 2 gets 5.
Okay.
Index finger, that's 5 for electrode 1, 3 for electrode 2. Middle finger is balanced 4 and 4. Ring finger is 3 and 5, like the thumb, interestingly. And the pinky is 2 and 4.
Wow, that's really specific. So those different number combinations, like 3 and 5 versus 5 and 3, that's what makes the signal look different for each finger.
Precisely. These aren't just random numbers. They're designed to create distinct electrical signatures for each finger's movement. It helps illustrate the principle that different muscle activation patterns create unique EMG waveforms.
Okay, that makes sense. It really drives home that different movements produce different signals.
Right.
But this brings up a critical point you touched on earlier. This is not real medical data, right?
Absolutely not. And that's probably the most important takeaway here.
Okay.
The purpose of this detailed simulation, the patterns, the noise, it's all geared towards one thing: providing an intuitive, accessible introduction to the principles of EMG. It's purely for education.
Right. So for someone wanting to learn about EMG, this sounds fantastic, but we need to be crystal clear. You wouldn't use this for any kind of real-world research or, say, medical diagnosis.
Definitely not. It is not intended for diagnosing neuromuscular problems, guiding physical therapy, or anything like that. It's a simulator, a
Yeah.
teaching aid. Think of it like a really sophisticated interactive textbook diagram, not a lab instrument.
That's a really important distinction to keep making. Educational tool, not diagnostic. Okay. So what about the future? Where does a tool like this go next?
Well, looking ahead, the developers have a clear vision. The focus is on keeping it simple, accessible, easy to use all on one screen.
Right.
And importantly, keeping it free from proprietary closed source stuff. Openness seems key.
Okay. Any new features planned?
Yeah, the really exciting part is they plan to incorporate other types of biomedical signals too.
Oh, like what?
Things like electroencephalograms, EEGs, brain activity signals, and electrocardiograms, ECGs, the heart's electrical signals.
Wow. Okay. So expanding beyond just muscles, that would broaden its educational reach quite a bit.
Massively. Imagine being able to interactively explore brain waves or heart rhythms in the same intuitive way.
That does sound powerful. Simulating brain activity, though, that must be way more complex than muscle signals, right? Are there unique challenges there?
Oh, undoubtedly. EEG signals are incredibly complex, influenced by so many factors. Simulating them meaningfully but simply will be a big challenge, but the potential payoff for learning is huge.
Yeah, I can see that. And you mentioned keeping it accessible. How are they managing that?
Well, on a practical note, the project welcomes feedback from users, and they also seek support through Patreon.
Crowdfunding.
Exactly. That support helps them enhance the features, improve the visuals, and crucially, maintain it as a free and open source resource for everyone.
That's great. Keeps it available for students, educators, anyone curious, really.
Precisely.
So let's kind of wrap this up. What we've seen in this deep dive is how a cleverly designed simulation can take something pretty complex, like EMG, and make it really accessible and, frankly, quite engaging for anyone. It turns these abstract scientific ideas into something you can actually play with and understand.
Yeah, it's a fantastic example of interactive learning.
Totally.
And maybe that leaves us with a final thought for you, the listener, to sort of chew on.
Okay.
Consider how tools like this, these interactive simulations, how could they change learning in other fields entirely? Imagine making quantum physics less abstract or complex economic models more tangible. It could really spark curiosity in ways we haven't even thought of yet, maybe fundamentally change how we learn new things.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.